Hi there, how is it going? First of all, I appreciate you being here and taking your time to attend the first Sonar Summit. And thanks, Sonar, for letting me present for you here. Let me introduce myself. My name is Mario Bastardo, and I'm a Sonar Bug Hunter at Exentia. Our team is called Sonar Bug Hunters because we make implementations of the SonarQube ecosystem for our clients, and three, we help them continuously improve their code in both quality and security. Likewise, we are partners of Atlassian, where we also help our clients improve their processes. I'm also part of the Sonar Navigators program, where we provide feedback to Sonar on features and procedures. And I usually contribute to the community too, sharing knowledge about continuous improvement. Today, we are going to talk about advanced SAST and several of the mechanisms Sonar provides to protect us against code defects. But first, I want to make a small introduction and explain how AI code differs from man-made code. Do you know what differentiates AI-generated code from man-made code? Exactly, nothing. I usually say that AI-generated code is man-made code with a few steps in between. Someone has to wrote the code, and then we train models with that code. So technically, it's the same code. But well, it's not that simple because there are quite a few differences between them. But from our point of view, they don't matter. Regarding code quality and security, reliability is reliability and security is security. Bugs are bugs, vulnerabilities are vulnerabilities. Let's define them because there may be people who don't know what they are. Bugs are those code defects that cause software not to behave as it was designed to. Something is not working as intended. Vulnerabilities, on the other hand, are code defects that allow attackers to gain control of our machines or steal our data, obviously without prior authorization. So we are going to analyze code as it really is, just code. But there is indeed a major difference that affects us. AI tries to give a plausible answer, one of many, and those answers can contain defects. AI does not perform that double check where we review our code and try to optimize it or look for defects. Models usually do not check for vulnerabilities, neither already documented ones nor the possibility of creating ones in the code they generate. And also, they tend to overuse dependencies. Dependencies included in standard language packages or frameworks may be overwritten by unnecessary ones. And trained models are prone to suggesting outdated dependencies, sometimes abandoned, and in other cases, vulnerable. I have to say these are common biases. Not every model does that, and some prompts can override them, and, etc. It's in a general way. So I'm going to introduce you three Sonar mechanisms that ensure code security, whether AI or human generated. First of all, taint analysis. Nowadays, at least during the last 40 years, when programming, we reuse code. So we call methods functions on and even other files. Sonar is able to analyze how code will be executed and therefore how data moves between our code. So as in this screenshot, we can see the execution flow. We can see the execution flow, a particular piece of data follows from its injection or introduction until it becomes a problem. until it becomes a vulnerability. In this screenshot, we can see how a user could call a URL in order to upload a file, and without any kind of control, is able to create that file in the application host. This could be a huge problem because it could lead to an LFI, local file inclusion vulnerability, and execute arbitrary code from our own machine. Okay, SCA. SCA stands for Software Composition Analysis. As you may know, we don't build applications only by writing our own code, but also by using packages made by other people, third-party scripts, and so on. These are called dependencies. Since we do not control those dependencies and just use them, some may contain undesirable features. With XCA software, we can check data associated with those dependencies and compare it with public vulnerability databases to know whether they are affected by any known vulnerability. Name, version, licenses, and transitive dependencies, the dependencies of our dependencies, are among that data. Sonar is also able to retrieve additional data that is not relevant for today's topic. And now, let me introduce Sonar Advanced Security. Sonar Advanced Security is the Sonar package for dependency analysis and control. In this screenshot, you can see the list of dependencies inside an app. In this other screenshot, I can show you one dependency and some of the previously mentioned features. Whether it's a direct dependency, one we added, or transitive, a dependency of our dependency. We can also show you the scope, whether it is used in production or in development, and we can show you the package manager. And if a package contains no vulnerability, we can rely on Sonar's traditional way of presenting information. As we usually say, Sonar is developers first and shows us why this is a vulnerability and provides quite a lot of information for us to decide how to handle the issue. We could see vulnerability info, how attackers could exploit it, severity, exploitation probability, and last but not least, whether this vulnerability has been publicly exploited. With this information, we may be able to decide how to approach this particular issue. Furthermore, Sonar also helps us to update the packages, telling us which versions are or are not affected by the vulnerability. As I said earlier, Sonar Advanced Security also analyzes and controls dependency licenses. In some cases, organizations may decide not to use certain commercial licenses for legal reasons. Sonar prevents us from using unauthorized packages. If one is used, Sonar warns us, as seen in this screenshot. CC BY 3.0 should not be used by our license profile. And we've reached the part of the talk where I speak badly about technology. Let's talk about the disadvantage SCA systems have in general. We've been saying that SCA checks for previously known vulnerabilities, and that's the main problem. The package or its code must be public. Someone must have discovered the vulnerability, and the discoverer has to have had the willing to document it. In summary, we only know vulnerabilities once they have already happened. So, we can check vulnerabilities introduced through our code before it reaches production. That is taint analysis. And we can also check known vulnerabilities in third-party dependencies, SCA. Doesn't the following step seem logical? Let me introduce Advanced SAST. Advanced SAST, previously known as deeper SAST, is taint analysis applied to dependency code. Let me explain. Advanced SAST is able to analyze where our data flows not only in our own code, but also inside dependency code. Advanced SAST can check where our code interacts with a package and knowing its internal code tell us whether that interaction leads to a vulnerability, not because of the library alone, but because of the combination of our code and theirs. We probably agree that some libraries by themselves should not be a potential risk. For example, a logging library is used just to show logs. But when the user controls the displayed data and that data is extracted from our company database, logging is not that fun, right? And how did we achieve this? Easy. Studies have shown that over 97% of every library used is open source. If we have access to the code, we can analyze it. And if we can analyze it, we can feed a database with the results. And if we have a database with those results, we can feed the taint analysis engine with them. It's a two-phase solution. On our side, we analyze open source libraries, up to 10,000 of the most popular ones today and growing. On your side, you use that data to detect whether your code is interacting dangerously with dependency code. In this screenshot, we can see a user control input that is propagated through the dependency, and inside the dependency, it becomes a vulnerability. And I want to showcase the first vulnerability ever discovered thanks to advanced SAST, but when we call it deeper SAST. This is CVE 2024 and that bunch of numbers. Jenkins, as you may know, is an open source project. Many projects like it are scanned in SonarQube testing to ensure not only that SonarQube works properly, but also to help the open source community when we find something. This code here executes a command introduced via a CLI. This function calls a method in a library called args4j, which parses parameters. This parse argument method ends up calling an expand at files method, and here is the problem. If one of the parameters passed to expand at files starts with an at, it is treated like a file on the file system. It can display any file the attacker wants. And if the attackers want etc password or etc shadow, magic, your machine is compromised. We could prevent the AI from making these mistakes. Conclusions. Someone or something has to check all written code. AI-generated code has some biases or some problems, and using AI makes them more likely to go unnoticed. Sonar has the ability to find vulnerabilities arising in our code, check known vulnerabilities in our dependencies, and check whether the usage of a library leads to a vulnerability. And that's it. Thank you very much for staying until the end of the talk. I hope it was helpful or at least entertaining. As I say, we are Exentia, and we are here for any questions or suggestions you may have. Gracias.